Welcome back to FSARPConf. We have our next speaker with us joining over Skype, John Azaria. John, I'll ask my usual question. Where are you right now? Where are we calling?
I'm actually en route to the UK. I'm speaking at Indicode tomorrow, so I'm in Indiana for tonight.
So just as I was getting into Redmond, you started running away from me. Is that right?
Pretty much. I'm sorry.
Yes. That's not very nice. Well, it's a virtual conf, so we can deal with speaker stars who travel all over the world. Cool. Do you know any good quantum jokes that I could make at this point? Probably no.
Yes and no.
That was good. All right, so I'll switch to your screen, and you can get started with your talk.
Fair enough. Let me know if the audio goes a bit wonky. It's hotel Wi-Fi, and also I seem to have a frog in my throat. So if you want me to repeat something, just say so.
All right, I'll keep an eye on things here, and let's get to your slides then.
Very cool.
And I'll hide my camera as well, so that we just see a little tiny picture of you in the corner. And you're on, ready to go.
Thank you. So you must have heard the whole buzz about Microsoft entering, or at least announcing that we entered the whole quantum computing thing. IBM's got a whole bunch of stuff going on. Google has everything. There's everyone and their dog is like trying to build qubits and make a big deal out of something. But Microsoft's approach was to actually look at the full stack of the quantum computer. And so at the top end of the stack, there's this whole problem of being able to describe quantum algorithms and be able to develop quantum programs and do it in a nice developer-friendly way. And so very serendipitously, I got involved in this project. I'll give you an overview of what actually happened, and then I'll walk through how Q#, the language, was actually developed and what role F# played in that. And hopefully this should serve as a kind of object lesson of F# in the wild, what functional programming strengths really are, and hopefully it might actually encourage someone to keep at doing what they're doing, right? So who am I? Well, so I've been a .NET practitioner since before it was .NET. I actually worked on what was known as COM+ back in 1999, before they called it .NET. I have a sort of weird history with languages. I actually worked on the visual J# .NET compiler, which was the .NET clean room implementation of Java. And so while I've been a professional C# developer and an F# enthusiast since about 2014 or so, I've had two kind of interesting things sort of going through my background. I built the whole enterprise software type stuff, but the back of my mind has always been a deep interest in programming languages and a deep interest in functional programming. So that's kind of the background to which I came to this picture with. As it turns out, I was working in Azure at the time, and somebody in the quantum team put out a tweet saying, hey, the quantum guys want someone interested in F#. And I didn't know anything about it, so I just retweeted. I didn't know anything about quantum, so I just retweeted the tweet and then went down to the quantum team to actually have a quick chat with the person who put the tweet out. And he told me about Liquid. Liquid was actually written by Dave Wecker, who is in our quantum research team. And it is a quantum simulator written in F#. And a quantum simulator is nothing but a library of linear algebra functions with the specific domain of quantum computing. So basically, it turns out that all of the quantumness of matter that we can talk about is quite accurately described using quantum mechanics. Using linear algebra. So we can define a set of libraries that allows us to model quantum mechanics in linear algebra, and then allow us to write programs on a computer that would perform those linear algebra operations for us. And that's in effect what the simulator does. And so Liquid was written. It was a very popular package. It was a brilliant piece of work. You wrote code in F#. Now, this is actually Liquid code, but it's really F# code, as you can see. And it's got the primitives for quantum. So, for example, H, which is Hadamard, and C0 over here, and M, which is measure. These are all functions that are quantum operations, which are effectively matrix multiplications. You express them in F#, and then they have an implementation which involves basically doing the math. And Liquid would simulate what the behavior of this system would do for you. As I said before, it was a brilliant piece of work. It was very widely used in academia. Lots of papers reference it. It's a very powerful simulator that you can just use. And the beauty of it was that it actually proved that F# was a powerful enough language to express quantum constructs. And then, so while this thing was being put in production and being used, and you can still download it from GitHub today, they were working on, and you'll pardon the pun because people in research have strange senses of humor. We had a product called Solid. Solid was, as opposed to Liquid, Solid was supposed to be the way in which you took the program that you wanted to run from the simulator itself, separate the simulator out, and be able to plug in a proper quantum computer. Because we were building a quantum computer, we are in the race to get a qubit. So at some point when the qubit is ready, well, we want to be able to program the thing. So they did what they knew best, which was to take F# code and use this really neat feature in F# called the reflected definition, which gives you the AST of the program that you're trying to write. And then you can then interpret the AST to do what you want in terms of saying, oh, this sequence of function calls is really a sequence that needs to be run on the quantum device. So we'll batch it up and send it down to the quantum computer to do stuff. Now, I'm going to stop here and point out something that isn't entirely obvious to everybody. A quantum computer will not, probably in my lifetime, will not run on your local machine. It won't run at room temperature. It certainly won't run on your desktop. A quantum computer turns out to involve using some really nifty physics, but most of the physics happens at very close to absolute zero. So what we'll end up doing is we have to build a fridge, and then we have to build this quantum device, kind of like your processor, that sits in the middle of this fridge, protected from stray radiation and so on and so forth. It's a very challenging science problem. It's an extremely challenging engineering problem, and it runs at about 20 millikelvin above. So basically 20 thousandths of a degree above absolute zero. So it's not likely that we're going to get that kind of infrastructure in our basements anytime soon. So what we will end up doing is always program the quantum device as if it was a coprocessor. And the coprocessor is going to perform computations that are going to be difficult for the main computer to do. And those computations in the quantum context are basically the linear algebra multiplications, matrix operations. Matrix operations, if you remember your maths and if you think about what they actually do, they're extremely compute intensive in a classical sense. Both in terms of compute and in terms of storage, you need to have enormous capacity on your machine to be able to do a bunch of stuff. Whereas the quantum devices kind of do those at much lower cost. So the goal is for us to be able to write a program that we want to separate out into two pieces. One that is going to run on the classical machine, and the other is the piece that's going to have to be shipped off probably across the cloud to something in a fridge that's about 15 millikelvin or 20 millikelvin, and is going to do the matrix multiplication for you because it's able to do that much faster then you could do it on your local machine. And that's a very hand-wavy way of explaining what quantum computation looks like. So the goal here in this example, for example, is still taking F-sharp code, but we have reflected definition, which gives us the AST of the EPR function, for example. So instead of actually just calling EPR and expecting it to be a function call, we go into the body of EPR and look into what it's trying to do and build up the set of sequence of instructions that needs to go and be executed on the quantum device. So what was the net result of that? Well, F-sharp's reflected definition is extremely powerful and extremely cool. It allows you to use F-sharp as a native language to express quantum computation. But then F-sharp turns out to be too powerful because you can write code that is correct in F-sharp, but has no meaning in the quantum domain. And that becomes very difficult to extract by just looking at the AST. Effectively, what you're doing is looking at the AST to try to determine the intent of what the person was trying to write, so that you can discover the quantum set of instructions that needs to be equivalent to it. Additionally, you have a conflation of type systems, so you'll end up having the ability to create complex types, for example, in F-sharp, which really have no meaning in the F-sharp in the quantum context. But of course, now we recognize that the quantum computer and the simulator are both really co-processors of a classical computer. And so there are two real programs that are interleaved. That's really the big message that came out of this. And at this point, they hired us to come in and take a look at Solid and try to make it work with a real quantum device. And that's the context in which I joined the team. And of course, if you've probably run into me a few times, you know that the Mword comes out fairly quickly. And it turns out that this turns out to be a very, very powerful and very, very useful way to think about quantum computation. So I won't launch myself into a full-blown monad tutorial at the moment, but fundamentally, what the idea of a monad is once you lift a value into this monadic context, you can then sequence a bunch of operations on top of that context without having to know the individual value, because the context is the one that's going to bind the operations and create the sequence for you. Now, this model of thinking about monads, this intuition turns out to be extraordinarily powerful because the quantum device is in effect modeling state that you cannot represent physically in a classical machine. And so when you make operations on the quantum device, what you're really doing is you can't get access to the state to actually do the calculations yourself. You are asking the quantum device to sequence the instructions for you, very much like a quantum monad. So, well, we basically took that concept and ran with it. And very quickly, instead of having to interpret everything and run, in a very performance resource constrained way, we wrote the thing out as a CE instead. So now we created this quantum monad thing, and then we were able to actually express the computations that you wanted to do on the quantum monad and chain the whole thing using the CE context, the constructs. And this turned out to actually be extremely powerful, very, very fast. There was examples where the solid approach of interpreting would have taken us 8 hours to do something, whereas the monadic approach landed up doing exactly that in about 300 milliseconds. So because we were able to remove the whole concept of reflection, remove the whole concept of interpretation, but still separate out the two contexts. So we know that something inside the quantum CE is actually in the quantum context from the thing outside. We were able to achieve a level of separation without sacrificing performance. Obviously, there's a cost that you come to it, and then that is one of the things is that the syntax becomes a little more cumbersome. If you look, you'll find that there's a whole bunch of quantum dot here and a quantum dot there. It tends to be a little bit of a nuisance. And then one of the things that turns out to be kind of useful is for us to be able to look at the sequence of instructions in the code and reason over them. So it turns out that you can actually compress sequences of instructions, for example, by just looking at them, which you won't be able to do if you're just executing the thing. So we landed up creating a new way of representing this. And one of the things that we did for this was recognize that this is really us trying to interpret something that is quantum. We were trying to interpret a sequence of quantum instructions. Well, if you've seen Scott Lashin's 13 Ways to Look at a Turtle, he introduces a very interesting concept. The concept of the interpreter pattern has a functional equivalent. And that functional equivalent turns out to be something known as the free monad. Now, the free monad is something that you can recognize basically if you come from a non-F-sharp background, because it turns out that you need to have a higher level of abstraction to be able to think about it and talk in terms of it. But the concept is actually quite useful, and you can actually implement the free monad in F-sharp. And so what we did was we separated out the language that the quantum instructions supposed to represent and put that into what is the free monad functor, and created a free monadic program and put a runtime in place as well, because the free monad turns out to be extremely expensive on stack. So we created a trampoline that allows us to do this. The paper for doing this is available. I'll give you the resources, and I'll give you the gist of the code as well. But now once you do that, you effectively haven't changed the syntax of what you're doing, except that the C naught and the H and the JM and so on are not quantum dot anymore. And this gives us also the ability for us to say, ask the sequence to represent it, to describe itself to us in the way in which it would run, so that we could then figure out what the costs of doing a computation, for example, are. But there are some severe limitations to this. What we've gained is we've formalized the operations that are native to quantum computing. We haven't sacrificed any performance for doing that. We can kind of reason over what the sequence looks like, but really we can't ask the program to analyze itself. We can't look at the whole program and get a sense of how many qubits it's going to take, or how long, how many sequence of operations it's going to run, and so on and so forth. But this was an improvement in terms of clarifying the approach that we wanted to take. I'll put these links up. I mean, the first one is actually the 13 Ways of Looking at a Turtle. The paper that we implemented was Runar Bjarnasen's paper of stackless Scala, but we put it in F-sharp. And this just actually contains the entire F-sharp implementation of the free monad. It's only about 150 lines long. I'm not going to walk through any of that, but it's just to give you an idea that F-sharp played a critical role in actually allowing us to crystallize our idea of what quantum computation was going to look like. So what we did at that point was we sat back and said, look, this monadic context is very important. What we need, though, is not just the monadic context, but the ability for us to be able to look at the monadic context and then reason over it, and also control the constructs in such a way that what belongs to the quantum domain doesn't get conflated with what's not inside the quantum domain. So we wanted to have an extra types universe that is only for quantum device. And we landed up needing to be able to retarget the quantum sequence wherever we wanted to do. So it turns out that what we did was we took the free interpreter and gave it some steroids. And a free interpreter on steroids is really a compiler. So we created a little programming language with its own syntax and the ability for you to now reason over the whole program, because the compiler can now build up a picture of what the thing looks like. and be able to execute that against the quantum device. So in some sense, we came back full circle in that we came back to the solid context, where what the idea was that we were going to interpret everything. But in doing so, what we've done is we've cleanly separated out what is F sharp from what is Q sharp. And the Q sharp piece can be reasoned about in the Q sharp compiler while it's being exercised in the host program. So if you think about this program, you can think about this as the CE's body with its own custom syntax, and the interpreter as effectively being a beefed up version of the compiler is basically a beefed up version of the interpreter of the monadic interpreter. And if you think that this thing looks imperative and side effectful, it is, because it's exactly that. It's actually performing side effects on the quantum device and on the quantum device only, because that's really the context in which this whole sequence is run. And in some sense, this justifies why we have a new language, because we needed to have this clean separation of universes so that the stuff that's running on the quantum context can be expressed idiomatically in terms of just that quantum context. So we were able to give it new syntax constructs like repeat until fix up, which turns out to be a very common pattern to use in quantum computing. And we're now able to run extensive whole program analysis on the whole program because we have full control of the compiler. So now you say, okay, you've got this whole thing, you've created a new language. How did F sharp help? How did F sharp play a role in it? Well, if you think about Q sharp, well, it's got some familiarity from C sharp. It's got braces and semicolons, and it looks kind of like C sharp. But in reality, it's actually very deeply influenced in its nature by F sharp. It's fully functional in the sense that functions and operations are effectively bare and unadorned, and you have first order functions, and everything is immutable by default. If you want something to be mutable, you literally have to do a very explicit thing by saying, hey, I want this to be mutable, and now I'm going to set the mutable thing over and over again. So it makes the code more ugly, and I think it's justifiably so. Of course, Q sharp has some interesting idiosyncrasies all of its own. For example, it allows for partial application, but not partial application like F sharp does, in that because we have a tuple in, tuple out kind of structure, you can pass in any number of the tuple constituents and partially apply. So you could apply, if your input arguments were 5 tuple of arguments, you could potentially carry in argument 1, 3, and 5, and it would return a function that would take the other 2 arguments and apply those. So there's a little bit of charm that we brought into its language by itself, but it's deeply influenced by functional languages, F sharp in particular. More to the point, F sharp is actually the tool that we use for the entire development process. The parser is implemented using fparsec, and we have quite a powerful parser now, all written in fparsec that does a lot of the heavy lifting. The compiler, in terms of the type checker and so on and so forth, all of that stuff is written in F sharp. The code generator actually uses another library that I wrote a long time ago to generate C sharp from F sharp. And that's written in F sharp. There's a Brightsword Roslyn wrapper library that you can go down and get at. And we generate all our C sharp code for simulation purposes with F sharp. And the document generator is entirely written in F sharp as well. So there's a bit of influence in terms of the tooling that we have that we use F sharp on a daily basis for. And of course, F sharp can be the host language. So we even have a sample where F sharp can be used to control the Q sharp sequence and actually get the quantum program to run from within the context of an F sharp program. So in summary, look, F sharp has been like instrumental in getting us to where we are, both in terms of the evolution of quantum computing as a as a growth pattern in Microsoft. Like we have a quantum computing effort that started off with the simulator, and through a host of very interesting, very functional sort of steps, landed up giving us a new language, which we then implemented using F#. And then, of course, the code generator for the simulation runtime and as a host language for the quantum computing itself. Both of those can be done using F#. And that's in effect, the tale of the two languages that has led to the quantum computing effort at Microsoft. So I'm happy to take further questions. Let me go back to the screen here and see if I can stop sharing the desktop maybe, or how does it work?
Yeah, just switch to the video. Yep, sounds good. Thank you.
Okay.
Yeah, and we do actually have some questions from people from F# Slack.
Excellent.
So the first question sounds like, what the heck is qubit, and why has the definition changed so many times since biblical days?
Oh, well, it all depends on who wrote the Bible, to be honest, in terms of qubit. So the qubit is, okay, so a bit is a binary structure that stores a binary value, okay? So binary value that you and I know is typically 0 or 1, right? But a 2-bit, in a two-level system, in a two-level binary system, you have 0 and 1. And a bit stores that information. So a bit string of size n can store, to actually store 2 to the n values, you need 2 to the n bit strings, right? Now, it turns out that from a quantum mechanical perspective, there's some interesting phenomenon that takes place. And one of the 2-bit systems that you get in quantum mechanics is you can basically get many 2-bit systems in quantum mechanics that exhibit a property known as superposition. And that property of superposition means that you don't just store 0 or 1, but you can store any linear combination of the 0 vector and the 1 vector at the same time. Okay? So the superposition principle basically allows you to store an arbitrary set of values. So in order to store 2 to the n values in quantum mechanics, you only need n qubits. You don't need 2 to the n bit strings. And because that difference is very large, you get a very big storage speed up for several algorithms using that approach.
The Froome and intrinsics.
Sound from the studio? Okay. So we have another question, which is,
Okay.
Could you say a few words about how Microsoft's specific approach is different to measuring qubits, differs from other players like D-Wave or Intel?
Wow. So this is going to stray far away from F# if we go down this road. So I'll give you the top level version, and really the conversation about what our quantum approach is like, I think is a different conversation than the one we're going to have that in F#, to be honest. But let me try to answer the question now. So it turns out that qubits are quantum mechanical devices that store quantum mechanical information are very unstable, and they are unstable for many reasons. Mostly because of interference with nature. So it turns out that the physical concept, the quantum mechanical concept of measurement is simply a function of how the system is being interacted with by another large system. So if you take a qubit and you let it interact with its surroundings, that surrounding is going to effectively measure that qubit and change its state. Okay?
Okay.
So one way of actually solving this problem is to change the environment so that you limit the amount of interference that you get. And one way to do that is to chill it very, very cold. And that's part of the reason why a lot of qubits actually work in the sub-millikelvin, the sub-Kelvin regime. So basically, you'll end up having, temperatures in the millikelvin region, and the amount of interference that you'll get from the outside is reduced significantly, so your qubits can stay alive for a little bit longer. There are other things that you can do, though. What Microsoft is doing is pursuing what is known as a topological qubit. The mathematics of this is actually well beyond me, so I can't explain it, but what I can tell you is something sort of analogous to topology. So if you think about a donut, and you think about the property of a donut as something that has a hole inside it, right? If you think about a donut that way, you could do quite a bit of twisting of a donut, for example, before that hole is not recognizable as a hole anymore. So you basically, that structure, as opposed to a ball, right? The moment you take a ball and you deform it slightly, it stops being a ball. But if you define a donut's donutness as the hole in the center, you can do a lot of things to a donut before it stops being a donut.
Cool.
And that means that the donut is actually more sort of topologically stable than a ball. And in some sense, the qubits that we're looking at are similar in that regard. They have a topological structure that is capable of taking a little bit more beating from the outside world without losing its qubitness. And in some sense, that's kind of the physical qubit is going to be different in that regard.
Cool. We have another question from Slack. A person is asking, I read the Q-sharp guide on the official site, and right now the classical part of the program has to be written in C#. I would like to ask if Microsoft plans to extend the support to other languages.
Oh, that's absolutely not true. Actually, there's nothing in the documentation that says that it needs to be written in C# at all. In fact, we have a demo written in F#, and that's kind of the point I was trying to make earlier, that you can continue to use F# in the host language of a program and write the quantum part in Q# and the host part in F#. We, in fact, have a demo of the hydrogen-hydrogen bond experiment written in F#. Cool. So it's definitely possible to use multiple languages to do it. There's even support for Python coming down the track. We had a demo earlier in Python, but once we moved to .NET Core, that sample doesn't work anymore. But we're working on trying to get support for multiple host languages to work.
Sounds good. Thank you so much. The talk was really interesting. We learned a lot about how some cool things are built with F#. And I will disconnect from the call. Thank you so much.
Thank you.
And right now, we probably are going to have a small break. And stay tuned for the next talk from Jeremy. And we're just going to have a small break.